Hi everyone, today we are going through a journey of mastering electrochemical supercapacitors from one of the best scientists in the field. I have summarized this book in a way that feels like listening will help us grasp and absorb the concepts from all the details, starting from the history of electrochemical supercapacitors to how they work, the theory behind their working, and the applications and the technological progress that we have made along the way within the last few decades. Imagine an 18th century scientist carefully holding a strange device, a Leyden jar, the first capacitor. Two metal conductors separated by a glass allowed static charge to accumulate on their surface. Astonishing early experiments. Back then it was called a condenser, and while everyone could see it stored electricity, nobody knew fully how. In fact, the elusive nature of how charge clung to surfaces led one chemist to compare the mysterious electric double layer to the phoenix. Everybody says it exists, nobody knows where it is. Yet, this surface charge effect was very real and would eventually give birth to the today's electrochemical supercapacitors. Fast forward to the mid 20th century, scientists realized that if you take that same principles of two charged layers and apply it at the interface of a porous electrode and an electrolyte, you can pack astonishingly more charge into a small volume. In 1957, General Electric's Becker filed the first patent for such electrical energy storage device using porous carbon in an electrolyte. He effectively described storing energy in the electric double layer at a carbon electrolyte interface, the core principle of all modern supercapacitors. Thus, a new class of electrochemical capacitors was born, marrying principles of surface science and electrochemistry. These devices could be charged and discharged rapidly, much faster than batteries, because they store energy without relying on slow chemical reactions. Early on, supercapacitors were mostly curiosities for labs and patent offices. But by the late 20th century, advances in materials, especially in high surface area carbons, metal oxides, and conducting polymers, made their capabilities soar. Researchers like Conway, who is the author of the book I'm trying to summarize, and Sergio Trassetti recognized that by using new materials with exceptionally large active surface areas, one could store many farads of capacitance per gram, millions of times the capacitance of a Leyden jar. Supercapacitors suddenly moved from theoretical interest to practical reality, bridging a crucial gap in energy storage technology. So, what exactly makes a supercapacitor super? It helps to compare it to its well known cousin, the battery. Both supercapacitor and battery store energy, but they do so in fundamentally different ways. In the next part of our journey, we'll contrast these two words, setting the stage for a deep dive into the science of double layer capacitance, pseudocapacitance, ion transport, electrode materials, and more. By journey's end, you will see how mastering the science in Conway's book empowers us to design devices that can charge in seconds and last for millions of cycles, all while delivering powerful bursts of energy on demand. The marathon versus the sprint, batteries and supercapacitors. Picture a battery and a supercapacitor side by side. Both are like energy reservoirs. But a battery is a marathon runner, delivering energy slowly and steadily, while a supercapacitor is a sprinter, unleashing energy in quick, powerful bursts. The difference comes from how they store energy. Batteries store energy in chemical form. During charging, electrical energy drives reversible chemical reactions. During use, those reactions release energy. This means a battery's voltage stays relatively steady during discharge until the reactants are used up. Think of a battery as a fuel tank. It provides a fairly constant push or voltage until nearly empty. Supercapacitors store energy electrostatically. No chemistry needs to occur. Charge simply accumulates on the surface of electrodes, balanced by opposite charge in the electrolyte. As a result, the voltage of a supercapacitor As a result, the voltage of a capacitor falls linearly as it discharges. Because the more charge you pull out, the less remains to sustain the voltage. Just as a stretched rubber band's tension drops as it relaxes. What does this mean quantitatively? If a battery and a capacitor are charged to the same voltage V with the same amount of charge Q, the battery can ideally deliver twice the energy. In a battery, energy comes from a chemical potential and is roughly given as energy equals to charge multiplied by voltage. In a capacitor, energy is equal to half of charge multiplied by voltage on discharge because the voltage drops with Q. This fundamental difference is why historically batteries have much higher energy density than supercapacitors. For example, one analysis in Conway's book compares a classic nickel cadmium battery cell to a carbon double layer capacitor. The nickel cadmium could store on the order of 225 watt hours per kilograms theoretically, whereas an electrochemical double layer capacitor of a similar weight stores only around 10 watt hours per kilogram. In other words, the capacitor held maybe 5 or 10% of the energy of the battery in that scenario. If you stopped there, batteries might seem superior to you. But the story flips when we look at the power and lifetime of supercapacitors. Supercapacitors can deliver massive power spikes and do so again and again for hundreds of thousands of cycles with minimal wear, where a battery's power is limited by how fast chemical reactants can diffuse and react, and pushing it too fast can cause heat and degradation. A supercapacitor's limitation is mainly the speed of charging the double layer and moving ions, processes that can be extremely fast. Conway notes that even in the 1990s, prototyping prototype supercapacitors achieved shockingly high power outputs. For instance, 30 kilowatt per kilogram in one 25-volt device using ruthenium oxide electrodes. This is tens of thousands of watts from a kilogram device, akin to draining a device in mere seconds. Even typical carbon based supercapacitors easily provide power on the order of 1 to 10 kilowatt per kilogram, far above most battery types. This makes supercapacitors ideal for tasks like capturing a burst of energy from regenerative braking or providing an instantaneous power boost to an electric vehicle. Cycle life is another big differentiator. Each time a battery charges and discharges, Its electrodes undergo chemical changes, phase changes, lattice strain, solid electrolyte interface formation, and other things which are happening during the electron transfer reactions in batteries as they charge and discharge, gradually wearing it out. A lithium ion battery might last a few hundred to a few thousand cycles before its capacity fades significantly. A supercapacitor, by contrast, stores charges by simple ion adsorption and desorption on surfaces, a non destructive physical process. There is no bulk crystal to break down with cycling. As a result, supercapacitors have excellent cyclability, often enduring 100,000 plus cycles or maybe 1 million cycles with negligible loss. In practice, they can last for decades, whereas a battery might need replacement every few years. This reliability is crucial in applications where maintenance is difficult or downtime is costly. To sum up, a battery is an energy warehouse. It holds a lot, but you can only get it out at a measured pace, and repeated heavy use ages it. A supercapacitor is an energy sprint champion, smaller energy reserve but capable of lightning fast charge and discharge, and it hardly ever tires out. These traits aren't in outright competition so much as complementary. In fact, many cutting edge systems marry batteries and supercapacitors. The supercapacitor handles the surges and buffers the battery from stress, thereby improving overall efficiency and lifespan in electric vehicles, grid storage, and more. Now that we have painted the big picture, it's time to dive into the scientific heart of supercapacitors. How do they actually store charge at the atomic level? What is this double layer we keep mentioning? And how do ions in a liquid form a capacitor with a solid electrode? To answer that, we'll travel back to some foundational science and then journey through modern advancements. The electric double layer, where physics meet chemistry. When a conductive electrode is immersed in an electrolyte solution and a voltage is applied, something remarkable happens at the interface. A double layer of charge forms. One layer is the excess charge on the electrode surface, electrons or electron deficiency in the solid, and the other is a mirror layer of oppositely charged ions in the liquid, crowding near the surface. This nanoscopic separation of charge, only a few angstroms or nanometers between the charge centers, creates an electric field and thus a capacitance, exactly like a traditional capacitor, but not at but on a molecular scale. In essence, the interface behaves like a tiny parallel plate capacitor where one plate is the metal surface and the other is a layer of ions in solution separated by a gap filled with molecules of solvents. The thickness of this effective dielectric is incredibly small, which is why the capacitance per unit area can be so high. How high? A typical smooth metal electrode in aqueous solution has a double layer capacitance of around 10 to 40 microfarads per square centimeter of surface. By itself, that isn't mind blowing, but consider a gram of porous activated carbon that has an internal surface area of 1000 to 1500 square meters. Thanks to the vast area, about the size of 4 tennis courts in a single gram, the total capacitance can reach on the order of 100 farads per grams or more. That's how supercapacitor achieves such extraordinary capacitances. They use materials engineered to present extremely high surface area, to the electrolyte, effectively assembling millions of tiny capacitors in parallel on all the internal nooks and crannies of the material. The concept of electric double layer has deep historical roots in electrochemistry. The first simple model was proposed by Hermann von Helmholtz in 1874. He imagined the double layer just like a parallel plate capacitor with two layers of opposite charges separated by a thin gap. Helmholtz's model was like a rigid fixed arrangement, a layer of ions stuck at certain distance from the electrode. But later, scientists realized the thermal motion of molecules would make things fuzzier. In the early 1900s, Louis Gouy and David Chapman introduced the idea of diffusion layer, where the layer of ions is not static but spreads into the solution with the highest charge density near the electrode and decreasing with the distance according to Boltzmann distribution. Essentially, they treated the ions like a cloud. Imagine a crowd of people near a wall. People pack at first and then thinning out further away due to thermal jostling. This Goic-Chapman model explained why capacitance could depend on factors like ion concentration and temperature. However, it assumed ions were point charges and could approach the electrode arbitrarily closely. In 1924, Otto Stern combined Helmholtz's idea of a closest approach layer with Goy-Chapman's diffuse layer. He reasoned that ions have finite size, so they can't pack right up against the electrode surface. Instead, there is a compact layer of solvent molecules and perhaps specifically adsorbed ions at a fixed distance, and beyond that, a diffuse layer of ions distributed by thermal motion. This became known as Stern model of the double layer, essentially a capacitor in series model, one small capacitor for the compact layer, one for the diffuse layer. Later in 1947, David Graham refined the picture further by distinguishing between ions that stick onto the surface and those that stay with their solvation shells at a distance. The resulting Gouy-Chapman-Stern-Graham model is still qualitative framework we use to describe the double layer. What does this mean in plain terms? When you charge an electrode negatively, positive ions from solution swarm toward the surface. Some water or solvent molecules might line up directly on the electrode like soldiers at attention, their negative ends facing the positive electrode if the electrode is positively charged, for example. These form the inner layer. Just outside, ions hover at their closest approach, perhaps touching the solvent layer. That's often called Helmholtz outer Helmholtz plane. Beyond that, other attached ions spread out in a diffuse cloud, balancing the charge. The end result is a separation of charge across only a few angstroms, storing electrostatic energy in the process. Conway's book vividly describes how, for many decades, the double layer could only be inferred indirectly. It was a theoretical construct that explained measurable properties like capacitance, how charge adsorbs, but scientists couldn't see it. Only with modern techniques did we start to directly probe this interfacial structure. But once the double layer's ability to store energy became noticeable per se, thanks to new materials with exceptionally extended surfaces, engineers quickly took interest. The double layer went from a passive curiosity of electrochemistry to the active ingredient of a high power energy device. It's worth noting that the double layer in a supercapacitor is conceptually similar to the dielectric layer in a conventional capacitor. In a normal capacitor, you might have a solid dielectric like plastic, ceramic, or oxide between two metal plates. When charged, positive and negative charges build up on opposite plates, and the dielectric's molecules polarize to sustain an electric field. In an electrochemical capacitor, the electrolyte itself is the dielectric, and the separation of charge happens at the interface by rearranging ions rather than shifting the polarization within a solid. In fact, Faraday himself had early inklings of this analogy. He spoke of dielectric strain and lines of electrical force in a charged condenser, ideas that map onto how we now understand the oriented solvent molecules and space charged layer in the double layer. There is, however, a key limitation: voltage. In a standard capacitor, you can engineer the dielectric to withstand large electric fields, several kilovolts per millimeters, for instance, so you can apply tens or hundreds of volts before breakdown. But in an electrochemical system, the voltage is limited by the electrochemical window of the electrolyte. Apply too high a voltage and the electrolyte will undergo electrolysis. Water splits into hydrogen and oxygen, or an organic solvent breaks down. For aqueous electrolytes, that practical limit is around 1 to 1.2 volts per electrode, because beyond that, water begins to decompose. This is why traditional aqueous supercapacitors operate at low voltages. Pushing to higher voltage requires either using non-aqueous electrolytes or designing electrodes that undergo some clever chemistry to extend the window. We'll explore that next, as the choice of electrolyte and operating voltage is crucial for improving energy density. Before moving on, let's recap in story form. We have a metal electrode, and as we charge it, its surface either gains electrons or loses them. Immediately, the electrolyte's ions respond. Opposite charges rush to the surface, forming a tightly packed layer. It's almost like a molecular dance. The electrode says, I have excess negative charge, and the positive ions in the solution answer, will gather around, but they can't quite touch the electrons. They stay a few angstroms away. This ultra thin gap with opposite charges on each side is our capacitor. The beauty of supercapacitors is that by using materials with enormous surface area, we create billions of such interfacial capacitors working in unison, boosting the voltage, non-aqueous electrolytes, and wider windows. One straightforward way to pack more energy into a supercapacitor is to increase its operating voltage. However, as we just noted, water based electrolytes severely cap the voltage due to water's decomposition around 1.23 volts. To break past that barrier, designers turn to non-aqueous electrolytes, typically around typically organic solvents with dissolved salts, or even fused salts known as ionic liquids. Using organic electrolytes, modern supercapacitors commonly reach around 2.5 to 2.7 volts per cell, and some ionic liquid based lab devices can operate at 3 to 4 volts. What's the trick? Organic solvents like acetonitrile or propylene carbonate have much larger electrochemical stability windows than water. For instance, acetonitrile with a suitable salt might be stable to 2.7 volts before it oxidizes or reduces. By pairing such solvents with salts whose ions are larger and less prone to decomposition, like tetraethyl ammonium cations and tetrafluoroborate anions, which are standard in commercial supercapacitors, we can significantly raise the cell voltage. In fact, combinations of various organic solvents such as acetonitrile, propylene carbonate, gamma butyrolactone, and salts like quaternary ammonium salts or lithium salts are chosen to optimize the voltage window. Some devices even reach about 3 volts with organics and ionic liquids, which are basically salts that are liquid at room temperature, composed of bulky ions, have been tested up to 4 volts, though often requiring elevated temperatures or trade offs in performance. However, these non aqueous systems come with their own challenges. One is conductivity. Water is an excellent solvent with high ionic conductivity when salt is dissolved, whereas many organic solvents have higher viscosity or lower dielectric constants, meaning ions don't move as freely and may form ion pairs. Ion pairing in low polarity solvents can reduce the number of charge carriers since cation and anion stick together, effectively lowering the ionic conductivity and capacitance. Engineers counteract this by choosing salts with bulky asymmetric ions and solvents with decent dielectric constant. For example, acetonitrile has a moderate dielectric constant and low viscosity, making it a popular choice that yields high power performance. Propylene carbonate has a higher dielectric constant but is more viscous. Sometimes mixtures of solvents are used to get the best of both, a tactic to reduce viscosity while still minimizing ion pairing. Temperature also plays a role. Lower temperature increase the viscosity and ion pairing, causing internal resistance to rise and power to drop. Anyone who has tried to start a car on a frigid morning knows that batteries struggle in the cold. Supercapacitors too will see reduced performance at lower temperatures for the same fundamental reasons: slower ion motion, higher resistance. Next time you try to start the engine of your car, remember this. In summary, non aqueous electrolytes unlock higher energy by allowing higher voltage at the cost of some increase in internal resistance and often complexity in ensuring safety and longevity. Safety because many organics are flammable. Nevertheless, they are a cornerstone of modern supercapacitor technology. Virtually all commercial ultracapacitors for automotive and industrial use contain organic electrolytes to get that 2.7 volts cell voltage and sweet spot. Research continues into new electrolytes, including ionic liquids, which are non flammable and have huge stability windows, though their viscosity can limit power unless heated or carefully formulated. There is also interest in gel polymer electrolytes and solid state designs for special applications, but the fundamental story remains finding an electrolyte that stays intact under a strong electric field so we can hold more energy in the double layer without blowing the cell's fuse. With the electrolyte and voltage in mind, let's turn our attention to the other side of the equation, the electrodes themselves. After all, the amount of charge we can store depends on the electrode's surface properties and what's happening on that surface beyond just plain double layer charging. Activated carbon, the workhorse electrode material. If supercapacitors had a mascot, it would undoubtedly be activated carbon. This form of carbon, typically made by charging organic material and then activating it, is used in the vast majority of commercial supercapacitors as the active electrode material. Why carbon? Because it hits a sweet spot of properties: high surface area, good electrical conductivity, good chemical stability, abundance, and cost effectiveness. Activated carbons commonly have around 500 to 2000 square meters of internal surface area per gram. All that microscopic surface in the form of pores and fissures is where double layer charge accumulates. As noted, high surface area is directionally proportional to capacitance. Specific capacitances for activated carbon range from 100 to around 300 farads per gram, depending on the material and electrolyte. A typical value is of the order of 150 farads per gram in aqueous electrolytes and about 100 farads per gram or slightly lower in organic electrolyte. Electrical conductivity. Carbon is a decent conductor, not as good as a metal but sufficient when well structured. It's crucial that electrons can move through the electrode with minimal resistance. Otherwise, the high capacitance cannot be fully utilized at high power. Activated carbons, being partly graphitic, provide pathways for electron transport. Stability. Carbon is generally inert across a wide potential range, especially in the absence of oxygen or strong oxidizers. In aqueous, neutral, or mild electrolytes, carbon doesn't corrode, it's chemically stable. Even in many organic electrolytes, carbon can handle the voltages involved without dissolving or reacting. Only at extreme potentials will carbon start to significantly oxidize or reduce. Abundance and cost effectiveness. Carbon can be made out from coconut shells, coal, wood, or synthetic polymers. It's relatively cheap per kilogram. I think it's between $3 to $5 per kilogram, especially compared to exotic materials like noble metals, which are like hundreds of thousands of dollars, hundreds or more than $1,000 per kilograms. This makes it viable for bulk energy storage products. Activated carbon is not a single uniform material but a whole family of materials. They can be tuned for pore size distribution, density, and surface chemistry. One common form of activated carbon cloth One common form is activated carbon cloth or carbon fiber, which can offer a controlled structure and is easy to integrate as an electrode. Another is activated carbon powders that are mixed with a binder and pressed onto a current collector to make an electrode film. A key aspect of carbons is their pore structure. The pores provide the internal surface, but if they are too small, some electrolyte ions might struggle to enter. Or if they enter, they do so slowly. It's just like a layman's picture, but of course, there are many things going on, like all the ions are surrounded with water molecules and they dehydrate, they try to penetrate into the pores, which are different sizes. Ideally, one wants a hierarchy of pores: micropores, which are less than 2 nanometers, to give huge surface area, but also some mesopores or macropores. So mesopores are between 2 to 50 nanometers and macropores are greater than 50 nanometers. Macropores, mesopores, and micropores, interconnected together, forming a hierarchical structure, act as highways for ions to quickly access the deeper micropores. Optimizing pore size distribution is an active area of research. Too many tiny pores can trap ions or exclude them. while too many large pores means wasted volume that isn't contributing much capacitance. The best carbons strike a balance, achieving high surface area that is largely accessible surface. Another interesting feature of carbon electrodes is their surface functional groups. Activated carbons often carry chemical groups on their surface: oxygen, hydrogen, sometimes nitrogen if treated, especially around the edges of graphene like planes in their structure. These can be things like hydroxyl, carbonyl, carboxyl, quinone like structure. These functional groups can influence capacitor behavior in two ways. They affect hydrophilicity or wettability. A more oxygenated surface is generally more polar and can be wetted better by aqueous electrolytes. In organic electrolytes, too many polar groups might actually be less ideal, but moderate oxygen can still help wetting. Number 2, they can participate in Faradic or redox reactions, introducing a bit of pseudo capacitive behavior, which or sometimes unfortunately a self discharge kind of characteristics. For example, quinone hydroquinone redox couples on carbon surfaces can store charge by reversible reaction like a tiny battery on the surface. This can boost the capacitance beyond the purely electrostatic double layer value, which sounds great, and indeed it can contribute some extra capacitance. However, if those groups undergo redox, they can also lead to drift in voltage or capacity fading after many cycles if the reactions aren't perfectly reversible. Conway notes that oxidizable or reducible impurities or functional groups on carbon can cause indirect Faradic processes and contribute to self discharge. Manufacturers sometimes heat treat or chemically treat carbons to remove unstable surface groups, or conversely, to introduce specific surface groups that might be beneficial for a specific application. There have even been patents on treating activated carbon to improve stability by capping certain functional sites. One notable variant of carbon materials is carbon aerogels and carbon nanotubes. Carbon aerogels are synthesized to have a highly uniform network of mesopores. They provide somewhat lower surface area but very good connectivity and low resistance. Carbon nanotubes have lower surface area per gram than activated carbon, but they have extremely high electrical conductivity and accessible surfaces. Research has shown electrodes made of aligned carbon nanotubes can achieve fast response and high power density because ions can easily access the tube surfaces and the resistance is low. In practice, nanotubes or graphene can be combined with activated carbon to improve conductivity or to provide structural support. To visualize an activated carbon electrode, imagine a sponge, but not one with big visible holes, rather one with microscopic pores like a fine coral structure. The electrolyte soaks into the sponge when we charge the electrode. Every internal surface pore develops its own little double layer, the carbon surface charges, and counterions in the electrolyte squeeze into the pore to balance that charge. If the pore is accessible, it will fill with ions and contribute to capacitance. If it's too narrow for ions or not well connected, it's like a dead end tunnel, surface area that might as well not exist to the electrolyte. So, a lot of the electrochemical engineering of carbon electrodes is about ensuring that maximum surface is effectively used. Achieving a real electrochemically accessible surface area close to the BET surface is challenging. Often the electrochemical area is less due to imperfect wetting of small pores. Improving that by pore architecture design adding conductive pathways, or using advanced carbons directly improve the capacitor's performance. In practice, making a carbon electrode for supercapacitor involves mixing the carbon powder with a binder like PTFE or PVDF, which hold the particles together, and sometimes a conductive agent like carbon black is conductive. If it's not graphitic enough, one might add a bit of carbon black to ensure good conductivity. This mix is coated onto a metal foil current collector or just fabricated as freestanding electrodes. Typical electrodes might be 100 to 200 micrometers thick layers of packed activated carbon and binder. Two such electrodes sandwich a separator soaked in electrolyte to form a cell. This simple, robust construction is one reason supercapacitors can last so long. There is no delicate crystal lattice or phase transition, just a porous carbon scaffold holding charges. Our discussion so far has been about double layer capacitance, the non Faraday charge stored by carbon's surface. But as we hinted with functional groups, there is another mechanism to store charge through fast, reversible chemical reactions, pseudocapacitance. And to truly master supercapacitor science, we need to explore pseudocapacitance and the special materials that exhibit it. Pseudocapacitance, when redox acts like a capacitor. Early supercapacitors were all about double layer, but researchers soon discovered that certain electrode materials can store charge via rapid redox reactions and yet behave much like a capacitor. This charge is Faraday, involving electron transfer or chemical change, but unlike a battery, it doesn't produce a discrete voltage plateau. Instead, the charge versus voltage relationship is more or less linear over a certain range, just as a capacitor would be. This phenomenon was dubbed pseudocapacitance. What does pseudocapacitance look like in practice? Often it is identified by the shape of a cyclic voltammetry curve. A purely double layer capacitor shows close to a rectangular shaped CV. Current is constant as you sweep voltage, indicating a constant capacitance. A battery shows sharp peaks or sloping plateaus from the onset of redox reactions at particular potentials. A pseudocapacitive material tends to show broad, relatively featureless humps or nearly rectangular shapes, indicating its upcharge steadily across a wide voltage window. For example, in the 1970s, Conwey and others studied noble metal oxide films like ruthenium oxide and noticed that the charge discharge curves were mirror image and smooth, akin to a capacitor rather than a battery. Tracity and Buzanka reported that hydrated ruthenium dioxide films exhibited a voltammetric behavior closely similar to that of a capacitor. That realization kicked off an intense exploration of pseudocapacitive materials. There are a few archetypes of pseudocapacitive charge storage: surface or near surface redox reactions. Here, ions from the electrolyte adsorb or intercalate into the electrode's surface layers and change the oxidation state of the material, but without forming a new phase. Because the reaction can spread out along the surface or into a thin film, it can respond quickly and continuously with voltage. Transition metal oxides like ruthenium oxide, manganese oxide, or nickel hydroxides can do this. For instance, ruthenium oxide in a proton containing electrolyte can reversibly switch between ruthenium plus 4 and ruthenium plus 3 oxidation states with accompanying uptake or release of protons or other cations to balance the charge. This reaction is spread throughout a hydrous ruthenium oxide matrix. So as you charge the electrode, more and more ruthenium sites are converted roughly in proportion to the applied voltage rather than all at once. That yields a pseudocapacitance under potential deposition or adsorption. On some metal surfaces, certain ions can adsorb or deposit at potentials more positive than their bulk deposition potential, forming a monolayer or so. This can behave capacitive in a limited sense. On some metal surfaces, certain ions can adsorb or deposit at potential more positive than their bulk deposition potential, forming a monolayer or so. This behave capacitive in a limited sense. A classic example is the underpotential deposition of hydrogen on platinum. The hydrogen adsorbs on platinum surface in a certain potential range, storing charge. It's a Faraday process where protons plus electrons form adsorbed hydrogen, but it can be smoothly reversible if limited to a layer. However, such systems are usually not practical for large scale devices. They're more fundamental to study certain phenomena. Conducting polymers or redox polymers. Conducting polymers like polyaniline, polypyrrole, polythiophene, and their derivatives can undergo doping and undoping, insertion or removal of charge compensating ions when their oxidation state changes. For example, polyaniline can exist in leucomeraldine, ameraldine, and pernigraniline states depending on how oxidized it is. As you charge a polyaniline electrode in acid, anions from the acid enter the polymer to balance the positive charge on the polymer chains. The polymer goes from a reduced form to an oxidized or doped form. These processes can happen over a range of potentials and can be fast, since only ions in and out and electrode delocalization along chains are involved, giving a capacitive like behavior. However, polymer cyclic voltammograms often show peaks corresponding to specific structural transitions. Some polymers or certain conditions yield a smoother, more rectangular CV, which is desired for pseudocapacitor use. The goal with polymers is often to have a solid state material that can store charge Faradically but rapidly. They also can offer higher capacitance per volume. The distinction between a pseudocapacitor and a battery can sometimes be subtle. It largely comes down to phase changes and kinetics. If the redox process involves a phase transformation, or is limited by solid state diffusion over significant distances, it will act more like a battery. If it's confined to the surface or thin film and highly reversible, it can mimic a capacitor. Tressetti famously articulated that pseudocapacitance requires a mirror image charging and discharging behavior, meaning the current response on charging and discharging are symmetric without hysteresis. This is indeed observed in good pseudocapacitive systems like hydrous ruthenium oxide or some polymer films. If there is significant deviation or peaks, this indicates some kinetic irreversibility or distinct steps. Why pursue pseudocapacitance, you might ask? The allure is greater capacitance and thus greater energy density in the same footprint. Carbon double layer capacitance might be, say, about 100 farads per gram, but a pseudocapacitive oxide might achieve several times that because each active atom can store multiple electron charges via redox. Also, pseudocapacitance can work in tandem with a double layer capacitance when the materials are combined. For example, a porous oxide will have both its redox capacitance and some double layer capacitance. However, pseudo-capacitive materials often come with trade-offs. They can have lower electrical conductivity, they may not have as high surface area, and they can undergo mechanical or chemical changes that limit the cycle life. So, a lot of research is about mixing pseudo-capacitive materials with carbon or nanostructuring them to preserve their advantages while mitigating downsides. Let's spotlight two major supercapacitor material classes that Conway's book discusses in depth: ruthenium oxide and conducting polymers. Ruthenium oxide, a case study in supercapacitance. Ruthenium oxide is often held up as a nearly ideal pseudocapacitive material in terms of performance, if not cost. Discovered to be pseudocapacitive in 1970s, hydrous ruthenium oxide can achieve extremely high capacitance. Conway's book documents that hydrous ruthenium oxide, prepared by a sol gel route and mildly heated, can reach specific capacitances up to 720 farads per gram in sulfuric acid electrolytes. This is an extraordinarily high value, roughly an order of magnitude greater than most activated carbons. Even anhydrous ruthenium oxide, more crystallized like those used for catalyst electrodes, showed 150 to 200 farads per gram, which is still excellent. Why is ruthenium oxide so special? It stems from its ability to undergo a continuous reversible redox involving protons. Ruthenium oxide plus protons plus electron going to ruthenium oxide and forming hydroxide. In simpler terms, during reduction, some ruthenium 4 plus in ruthenium oxide accepts electrons to become ruthenium 3 plus, and charge balancing protons insert to form hydroxide with oxygen. Upon reoxidation, those protons leave and the ruthenium goes back to ruthenium 4 plus. Importantly, the hydrous form of ruthenium oxide, the structure is like a hydrated gel, allowing protons to diffuse in and out readily and uniformly. Not all ruthenium sites switch valence. As Galizioli and Tressetti noted, only a fraction tied to the oxide's non-stoichiometry might be electrochemically active, but enough are active over 1 volt range to store a lot of charge. Because this process doesn't produce a new phase, it can happen concurrently throughout the material. The CV of hydrous ruthenium oxide is nearly rectangular, indicating a broad capacitor-like charge storage rather than a sharp reaction at a fixed potential. Historically, ruthenium oxide was known as a catalyst. It's used on certain anodes for chlorine production. Those catalytic ruthenium oxide coatings, often on titanium mesh, are crystalline and mostly serves as conductive surfaces. But in the early 1980s, Conway and colleagues, and separately Tressetti's group in Italy, realized that hydrated ruthenium oxide can be a proton sponge and hold charge. They prepared it by, for example, depositing a hydro electroplating or chemically depositing a hydrous oxide film. As the film was cycled electrochemically, it grew in capacitance initially, indicating more active sites being accessed or created. The more hydrated and dispersed the ruthenium oxide, the better the pseudocapacitive performance, since water in the structure facilitates proton transport to all ruthenium sites. One fascinating aspect in Conway's book is the comparison between thermally formed ruthenium oxide and electrochemically formed hydrous ruthenium oxide. The former is crystalline, dense, and has more double layer capacitance plus some pseudo capacitance. The latter is porous, hydrated, and shows much more pseudocapacitance. For example, specific capacitance of a sol gel derived hydrous ruthenium oxide could be 720 farads per gram, whereas the calcined crystalline might be a few hundreds at best. The obvious drawback of ruthenium oxide is cost and abundance. Ruthenium is rare, precious metal. It's not economically feasible for large scale energy storage. Imagine building a car out of ruthenium, the cost would be astronomical. Nevertheless, ruthenium serves as a benchmark. It taught researchers what was possible and spurred the research for cheaper analogs. Efforts were made to find other oxides that can mimic this behavior, for example, manganese dioxide, nickel oxides, hydroxides, cobalt oxides, etc. Manganese oxide is much cheaper and has been used in some supercapacitor designs. It has a decent pseudocapacitive behavior, not as ideal as ruthenium oxide, and usually only in a narrow potential range before it becomes battery like. Nickel hydroxide is actually the basis of nickel cadmium battery electrodes, but in certain forms, nanostructured nickel hydroxide or nickel oxide, it can act pseudocapacitive near its lower potential range. Another idea has been to combine ruthenium oxide with carbon, either by mixing them or depositing ruthenium oxide on carbon to leverage the high capacitance of ruthenium oxide and the high surface area and conductivity of carbon. Conway mentions such composite approaches. Typically, a little ruthenium oxide can dramatically boost capacitance of carbon. But again, one must weigh the cost. In any case, ruthenium oxide stands as a brilliant example of turning a redox reaction into a capacitive reaction. If we had a cheap, abundant material that could do what ruthenium oxide does, supercapacitors could rival batteries in energy content. That remains a bit of a holy grail in this field. Conducting polymers, flexible electrodes with Faradaic flare. The other major class of pseudocapacitor materials is conducting polymers, sometimes called synthetic metals, because of their electrical conductivity. Examples include polyaniline, polypyrrole, polythiophene, and its derivatives like P dot. These polymers can electrochemically be oxidized or reduced, which adds or removes charge from their conjugated backbone. To maintain charge neutrality, ions from the electrolyte enter or exit the polymer matrix as counterions. This de-doping process stores charge. Polymers have some attractive features. They are relatively light, can be processed from liquid precursors, and some can achieve high capacitances. For instance, polyaniline in its most capacitive regime in acid electrolytes can reach on the order of 150 to 300 farads per gram, which is competitive with carbons. Polypyrrole and P dot have shown around 100 farads per gram in various setups. These numbers depend a lot on how the polymer is prepared, the size of the electrodes, the thickness of the electrodes, and the other exact conditions. The challenge with conducting polymer is often stability and the multi-step nature of their redox. Taking polyaniline as an example, in a strong acid like sulfuric acid, its CV typically shows multiple peaks corresponding to transitions between leucomeridine, emeraldine, pernigranulene forms. Each of those is a distinct redox step, not a completely smooth continuum. So polyaniline doesn't give a perfectly rectangular CV, it has bumps. However, if cycled in a limited potential range, it can behave more like a pseudocapacitor. Also, some derivatives or copolymers can have more smeared out transitions. For example, Conway's work with O-anisdine produced a polymer that showed only one broad peak, that is, a more capacitive like response. By contrast, something like poly P toluidine barely showed any Faradic peaks, but that was because it hardly stored charge. These nuances highlight that polymer structure heavily influences the electrochemical behavior. A big advantage of polymers is price and processability. They are made of common elements, carbon, hydrogen, nitrogen, and can often be deposited from solution or by electropolymerization. One can coat a current collector with a polymer film easily by electropolymerization, simply by running a current in a monomer solution. You can grow a polymer film directly on the electrode. This makes fabrication straightforward. Polymers are also mechanically flexible, which is useful for wearable or flexible energy storage devices. However, conducting polymers often suffer from cycling stability issues. The repeated insertion and removal of ions cause the polymer to swell and shrink. This can lead to cracking or loss of adherence to the current collector over many cycles. Also, some polymers like polyaniline have finite lifetime because over many redox cycles, side reactions or over oxidation can occur. Consequently, while a carbon supercapacitor might do 100,000 cycles with less than 5% loss, a conducting electrode might start to fade after a few thousand cycles unless carefully managed. Researchers try to mitigate this by using composite designs, for example, polymer coated on carbon fibers. The carbon gives a scaffold that supports the polymer and maybe reduces strain. Polymers often have lower electrical conductivity than carbon, so a polymer electrode might need a conductive additive or very thin configuration to ensure fast electron transport. All that said, polymers are promising for applications where energy density is more crucial than ultra long cycle life or extreme power. They can potentially store more charge in a given volume than carbon, since they can have battery like multi electron redox, and new polymers or redox active organic molecules are being developed that could bring pseudocapacitance to new insights. For example, there are quinone based polymers or other redox polymers designed to have fast kinetics and cycling. In summary, conducting polymers provide a way to achieve pseudocapacitance with organic materials. They complement the inorganic oxides like ruthenium oxide. Each has pros and cons. Oxides often have stable cycling but are heavier and sometimes costly. Polymers are light and cheap but can degrade faster. A lot of effort goes into hybrid devices, for instance, a carbon electrode with a bit of conducting polymer deposited on it, combining double layer and pseudocapacitive storage. Now that we have explored materials and mechanisms, double layers on carbons, pseudocapacitance on oxides and polymers, let's consider how all these factors come together with a real supercapacitor when a real supercapacitor is charged and discharged. That means looking at ion transport, internal resistance, and how to maximize performance. Essentially, we have to think about the device not just at equilibrium but dynamically. How fast can it store charge and what limits that speed? How fast can it charge and what limits that speed? Ion highways and resistive roadblocks, dynamics in porous electrodes. A supercapacitor's strength is how quickly it can charge and discharge, but that speed is not unlimited. The bottleneck is usually the movement of ions through the electrolyte and into the pores of the electrode, as well as the resistance of the electrode material and contacts. Understanding these limitations is key to designing capacitors with both high energy and high power. Consider a porous carbon electrode being charged. Initially, when you start charging, ions near the outer surface of the electrode respond almost instantly, forming a double layer and giving some quick capacitance. But to utilize the deep surface area in the interior pores, the ions have to diffuse inside those pores. This takes a finite amount of time. If you try to discharge the capacitor in a split second, you might only tap the charge on the outer surfaces because the inner charges haven't had time to contribute. It's like only emptying the mouth of a well because the water deeper down can't rush out fast enough. In frequency terms, the inner pores might not be able to charge and discharge at high frequencies. Electrochemists often model a porous electrode as a network of distributed RC elements, conceptually a transmission line of capacitance and resistance. Each incremental segment down a pore has a bit of solution resistance and a bit of capacitance. The result is a frequency dependent response. At very high frequencies, the capacitor might look like it has only a small capacitance, just the outer surface. At lower frequencies, that is, slower operation, the deeper capacitance comes into play. This is observed in impedance measurements. A Nyquist plot might show a 45-degree line, Warburg diffusion line, at intermediate frequencies, reflecting the distributed resistance of ion diffusion in pores. At very low frequency, the plot becomes vertical, indicating the full capacitance is accessed. Designing around this involves multiple strategies: optimizing pore size distribution, thin electrodes versus thick electrodes, higher electrolyte conductivity, particle size, and packing additives. Let's discuss this one by one. Designing around this involves multiple strategies. Optimize pore size distribution, thin electrodes versus thick electrodes, higher electrolyte conductivity, particle size, and packing additives. Optimize pore size distribution. As mentioned, include some mesopores to shorten diffusion distances. If every pore is dead end micropore accessible only via a long narrow path, that's a high diffusion resistance. Thin electrodes versus thick electrode. A thicker electrode stores more total charge, but ions have to travel further from separator into the interior. There is a trade-off between energy and power here. Higher power supercapacitors often use some thinner electrodes than an energy optimized design. Similarly, very high frequency or ultra capacitors might go to extreme thinness at the cost of needing more cells in parallel for capacity. Higher electrolyte conductivity. Using electrolytes with high ionic strength, good conductivity, and maybe even filling the pores well. A high conductivity electrolyte means less ohmic drop as ions move. The IR resistance, current times resistance, is what causes the voltage sag when drawing high current. Particle size and packing. In a composite electrode, small particles expose more surface but can also pack tightly and hinder ion flow between them. Some designs use mixed particle sizes to create a bit of void fraction for easier ion percolation. Others use aligned structures to make straight pathways for ions. Additives. Sometimes a little surfactant or functionalization helps electrolyte wet the pores better. Good wetting is crucial because any dry pore is lost capacitance. Conway's book enumerates ideal properties for high performance electrodes, which read like a checklist for mitigating resistances. Extremely high surface area and an optimized pore structure that minimizes internal resistance, and good electrical conductivity and strong mechanical integrity so you can form it into an electrode, and so on. In fact, let's summarize some of those key design criteria for electrodes. Maximum real surface area. Ideally, all of it all of it usable for double layer or pseudocapacitive storage. Think 1000 plus square meters per grams of accessible area. Optimal pore size distribution: pores large enough to allow fast ion transport but small enough to give lots of surface. A combination of mesopores for ion highways and micropores for storage is best. High electrical conductivity, both within the active material and through the electrode structure. Lower ionic resistance ensures even the fastest electrons can move without significant voltage drop. Good wettability by the electrolyte. The electrolyte should penetrate and remain in the pores easily. Surface chemistry may need to be adjusted for this. Electrochemical stability. The material shouldn't participate in unwanted reactions in the operating voltage window. For double layer carbons, that means resisting oxidation or reduction of the carbon itself. For pseudocapacitive materials, stability of repeated redox cycling without dissolution or structural breakdown. Mechanical integrity. The electrode should hold together and not pulverize or detach with cycling or handling. It also shouldn't expand or contract too much. Minimal self-discharge. That often ties back to the surface chemistry. Absence of reactive functional groups or impurities that can create internal leakage currents. This also relates to purity. No residual catalyst metal ions that could shuttle between electrodes. No single material perfectly ticks all these boxes, but the combination of advanced carbons and perhaps a touch of pseudocapacitive component is currently the go-to solution. Carbon is great on many of these, but improvements are sought in conductivity and in adding pseudocapacitance for more energy. Now let's talk about how we evaluate a supercapacitor's performance quantitatively, that is, the key metrics like energy density, power density, and how are they measured. Energy, power, and performance metrics. From a user's perspective, a supercapacitor's performance is summarized by a few numbers. Capacitance in farads tells how much charge it can store per volt. Often Q equals to CV gives a single value at a single frequency or DC measurement. Energy density, typically in watt hours per kilogram, gravimetric, and or watt hours per liter, volumetric. This tells how much energy the device can store relative to its weight or volume. Power density, in watts per kg or watts per liter. This tells how quickly that energy can be delivered. Equivalent series resistance. The internal resistance in ohms. A lower internal resistance or ESR means higher power capability and less energy lost as heating during fast charging discharging. Cycle life. How many cycles of charge discharge the device can endure with minimal degradation, often 80% of remaining capacitance. Self-discharge rate. How quickly it loses voltage when sitting idle, often given as a time to drop to a certain percentage or a leakage current in microamps. Capacitance is often measured by a galvanostatic charge discharge, charging at constant current and seeing how many coulombs it takes to raise the voltage by a certain amount. Because for an ideal capacitor, one can compute C from the slope of a voltage time curve during discharge. In a laboratory, one might see a specification like C equals to 100 farads, but note capacitance in supercapacitors can depend on time scale of measurement. Often a value is given at a low frequency, which is the full accessible capacitance. Energy stored in a capacitor. If the capacitance were constant, half CV square. In practice, if C varies with voltage, you'd integrate So I'm just trying to see how can I explain this in the audio form. It goes mathematical, it gets more mathematical, but try to extract and learn as we try to understand or visualize from this audio. Energy stored in a capacitor. If the capacitance over constant half CV square, in practice, if C varies with voltage, you'd integrate E equals to integral from 0 to V CV into V dV. But assuming near constant capacitance within the operating range, normal formula, which is half CV square, is used. So to maximize energy, you want both high capacitance and high voltage. That's why using organic electrolyte can significantly raise the energy even if C might be a bit lower in aqueous. For example, doubling the voltage quadruples the energy, which usually more than compensates for any drop in capacitance value. That's evident in prototype all ruthenium oxide capacitors. Even with moderate capacitance at 25 volts, it achieved 8.3 watt hours per kilogram, which is quite high for a capacitor, thanks to that high stack voltage. For context, commercial supercapacitors today might have around 5 to 10 watt hours per kilogram of energy stored in them. Back in the 90s, numbers like 2 to 6 watt hours per kilograms were reported. Those are lower than batteries, which can go up to 150 watt hours per kilogram. But the gap narrows if you consider usable window or power limited scenarios. Power. Power in a capacitive system is limited by internal resistance and by the fact that voltage drops as you discharge. The peak power output occurs when the load resistance equals the internal resistance. The peak power output occurs when the load resistance equals the internal resistance, the impedance matching condition. At that point, half the voltage is dropped internally and half across the load. The formula for maximum power is P equals to V square 4R ESR. I think there is some problem with that, but yeah, the normal formula which we use for to calculate the power density of capacitor. Um, so a low ESR is key to for high power. For instance, if a cell is 2.7 volts and has ESR equals to 0.01 ohms, then maximum power could be 182 watts for that single cell. Some high power designs boast milliohm level ESRs. Conway noted power densities of existing capacitors being well above those of nickel cadmium or lead acid batteries. Nickel cadmium might deliver maybe 200 watt per kilogram, and electrochemical capacitors can do several kilowatt per kilogram easily. In fact, that 30 kilowatt per kilogram example we gave is extreme but illustrates the point. One interesting nuance: because the capacitor's voltage drops linearly with discharge, if you want to use the energy between 2.7 and 1.3 volts effectively, you may need DC to DC converters to maintain steady output. Cycle life. Cycle life for supercapacitors is typically so high that it's not a limiting factor in most cases. They might be rated for 500k cycles or more. Wow. However, high temperature can age them, so sometimes a life spec is given like 10-year life at 65 degrees Celsius or such. Self-discharge. Supercapacitors, especially those with aqueous electrolytes or with pseudocapacitive components, can self-discharge faster than many batteries. This is usually due to internal leakage currents. For carbon EDLCs, self-discharge might manifest as a few percent voltage drop per day. Mechanisms include redox shuttle reactions, impurities cycling between oxidized reduced states and carrying charge across, and charge distribution especially just after charging. The voltage may drop as charge evens out inside porous electrodes. Though that component might recover if left open circuit. Interestingly, a phenomenon called self-potential recovery. Conway describes multiple mechanisms, including activation controlled Faradic process and diffusion controlled leakage. For example, if there are trace amounts of redox couple in electrolyte, it could continuously discharge the capacitor internally by shuttling electrons, or functional groups on carbon might slowly react. Self-discharge is measured by either noting voltage decay over time at open circuit or by leakage current under constant voltage. Engineers mitigate self-discharge by high-purity manufacturing, sometimes adding electrode balancing or voltage management circuits when multiple cells are in series. So one cell that self-discharges faster doesn't drag the others into reverse or overvoltage. Finally, how do these metrics interplay? A common visualization is the Raycon plot, which Conway discusses. This is a log-log plot of energy density versus power density. It shows the trade-off: at higher power, faster discharge, you get less energy out because of voltage drop and incomplete utilization of deep capacitance. Batteries occupy one region, moderate power, high energy; capacitors another, high power, lower energy. There is a smooth continuum. Supercapacitors fill the niche of high power demands. Interestingly, improvements in supercapacitors have been pushing their energy up, and some new battery technologies push power up, but the fundamental differences remain. So there's a lot of work that has been going on hybrid supercapacitors, in which people are trying to use the high energy density of batteries and the high power density of supercapacitors. But again, it's just an area of research. People are trying to increase the technology readiness level and improve the performance from lab scales to commercialization. But the main problem again comes at the cost of materials and the cycle life or lifetime of materials. Conway summarizes tables from mid 90s. For example, Panasonic's carbon capacitor 2.5 watt hours per kilogram, Maxwell's 6 watt hours per kilogram, with power densities in kilowatt per kilogram range. Those numbers have only modestly improved with newer carbons and such. A state of the art carbon supercap might be 10 watt hours per kilogram and 10 kilowatt per kilogram peak power. Okay, so these numbers are very interesting to remember. That state of the art supercap might be around 10 watt hours per kilogram and 10 kilowatt per kilogram of peak power. A lithium ion battery is around 200 watt hours per kilogram and 1 kilowatt per kilogram. So power density of supercapacitors is almost 10 times better, but they have almost 20 times lower energy density. So depending on what you need, burst of energy versus sustained energy, you choose one or the other or hybrid. Having covered the fundamental of how supercapacitors work and how we characterize them, let's not forget the practical side. How do you actually assemble one of these devices, and what does the landscape of applications look like? We'll conclude with some insights into practical construction, real world usage, and the technological developments that have brought supercapacitors from laboratory curiosities to vital roles in modern energy systems. Building the device. Practical design and evaluation. A supercapacitor cell at its core is simple: two electrodes, a separator, and an electrolyte, much like a battery in structure. But the devil is in the details of materials integration and manufacturing. Electrode fabrication. Activated carbon powder is mixed with a binder and sometimes a conductive additive if needed to form a slurry. This slurry is coated onto a current collector foil. Common current collectors are aluminum for positive and negative in organic electrolyte systems. Aluminum is stably in the roughly neutral pH of organics. The coated foil is dried and often calendared to compact it to a certain density and adhesion. The result is a sheet of electrode material. For high power, thinner coatings are used. For high energy, thicker but to pack more material but at a high cost of higher internal resistance. Separator. Between the two electrodes is a separator, typically a porous polymer film like polypropylene or cellulose based paper that allows ions to pass but prevents any electrical contact between the electrodes. The separator must be thin but not so thin as to risk shorting or tearing. It also should hold electrolyte well. Electrolyte filling. The cell is then filled with electrolyte. In manufacturing, cells might be vacuum filled to ensure all pores are saturated. The electrolyte volume needs to be sufficient to wet everything, but excess just adds up. Cell packing. Cell packaging. Supercapacitors come in various form factors: small coin cells, larger cylindrical can cells, or even pouch cells. In each case, the cell is sealed to prevent drying out or contamination. In large modules, multiple cells are connected in series to achieve higher voltage. For instance, a 12-volt supercap module might have 6 cells of 2.7 volt in series, plus some overhead. Balancing circuits are often included in series stacks to ensure one cell doesn't get overcharged relative to others. Without balancing, due to slight leakage differences, one cell could drift to a higher voltage while others go lower, which could push it into failure. Some designs simply use passive resistors to bleed current and equalize. More advanced ones use active balancing. Evaluation and testing. Manufacturers test capacitance and ESR typically via methods like constant current charge discharge or AC impedance at 1 kHz. They also test leakage current after a charge. Long-term life tests involve elevated temperature storage and cycling. For example, a spec might be capacitance will not decrease more than 20% after 500,000 cycles at 25 degrees Celsius or something along these lines. Supercaps generally might meet those easily. Quality considerations. Purity of materials is huge. The presence of any stray reactive chemicals can cause gas evolution or self-discharge. Many supercapacitors in organic electrolyte have a relief vent in their can because if they are abused or over voltage, the electrolyte can decompose and generate gas, and the vent allows it to escape safely rather than rupturing violently. Thermal management. In high power applications, even the small ESR can cause heating if cycles are very rapid. For instance, delivering 100 amps through 0.01 ohms is a 10 watt loss, which can heat a cell. In stringing many cells, ensuring they can dissipate heat or operating within duty cycles that allow cooling is considered. Stacking with batteries. One practical approach is pairing supercapacitors with batteries. For example, an electric bus might use lithium-ion batteries for steady energy supply and a supercapacitor bank to absorb braking energy and supply acceleration surges. The control system manages flow such that the supercapacitor handles fast transients, preserving battery health. Now, speaking of real world use, where do we find supercapacitors? As of Conway's 1999 perspective, supercapacitors were breaking into a few niches: memory backup, Small supercapacitors were used on computer boards, VCRs, etc. to maintain memory or clock when power is off for a short time. They replaced batteries in some cases because they are maintenance free and last indefinitely for trickle backup. Power conditioning. They were used in electronics where a short pulse of high power is needed. For example, camera flash units. Also, smoothing power in UPS or in renewable energy systems to buffer fluctuations. Transportation. This is a big one. Pioneering work was done to use supercapacitors in hybrid vehicles and electric vehicles. For example, Isuzu in the 90s worked on a bus that used supercapacitors for acceleration assist. Honda and Toyota experimented with assisted regenerative braking. Trains and trams in some cities employed supercap banks at stations to capture braking energy and then boost acceleration of departing trains. Even today, some modern trams use supercapacitors to quickly charge at stations to power them to the next step. Military and aerospace. The high power density is attractive for radar pulse power, laser pulses, and actuator power. Maxwell Labs developed ultracapacitors for particle accelerators and laser power sources where very high power in short bursts is needed. The mention of 30 kilojoules per kilogram in weapon system alludes to such specialized high power units for military pulsed power. Grid and renewable support. Even in the 90s, projects considered supercapacitors for smoothing wind or solar output over short intervals or for providing burst power to stabilize grid frequency. They respond faster than batteries or generators, so they can bridge the gap in the first few seconds of disturbance. Conway's Conway outlines the progression and the patent landscape from the first patent in 1957 through the 1960s and 70s, where companies like Standard Oil of Ohio filed patents but found no immediate market, to the late 70s and 80s, where companies in Japan commercialized small capacitors for electronics, and into the 90s, where automotive interest drove rapid improvements and flurry of patents worldwide. By 1995, as listed in one of the chapter, various developers had devices with few watt hours per kilogram energy and demonstrated the feasibility in vehicles and other systems. It's clear that supercapacitors emerged as a technology because the fundamental science was ready. Sergio Trassetti quipped that it was an example of technological innovation pushed by fundamental knowledge rather than vice versa. Scientists have spent decades understanding the double layer, and once the materials were available to exploit it, the technology blossomed. Conversely, it also needed a push from application requirements to really take off in R&D from after 90s. As of today, supercapacitors continue to improve incrementally. Newer carbons, better electrolytes, and novel hybrid concepts are bridging some gaps between batteries and capacitors. But the fundamental principle we have discussed remain the guiding light. Epilogue. The supercapacitor's promise. We have traveled from rubbing amber in antiquity to the Leyden jar to the refined science of the electrical double layer and pseudocapacitance. We have seen how Conway's book maps every layer of this story, the physics of charged interfaces, the nuances of different materials, and the engineering needed to turn chemistry into practical device. Supercapacitors stand today as a testament to interdisciplinary mastery, where electrochemistry, surface science, and materials engineering converge. They teach us that sometimes the old ideas like capacitance on a surface can find new life with a twist of technology. Listeners might be intrigued to know that even as batteries grab headlines in the energy storage world, supercapacitors quietly serve in the background whenever quick bursts of energy are needed reliably. From keeping the memory in your phone alive for a split second during a battery swap to powering the regenerative braking in the latest hybrid bus to stabilizing the power grids against fluctuations. The story is ongoing as researchers worldwide hunt for the next breakthrough, maybe a new pseudo-capacitive material as cheap as carbon but with the punch of ruthenium oxide, or solid state ionic conductors that allow 5-volt swings. The foundational knowledge of Conway's work will continue to guide progress. In the spirit of Richard Feynman's curiosity driven narrative, there is plenty of room at the surface. The molecular dance of ions and the electrons at the interfaces holds the key to energy challenges that affect us all. By mastering the concepts in electrochemical supercapacitors, scientific fundamentals, and technology applications, we are not just learning about one device, we're gaining insight into the whole realm of physics and chemistry that underlies modern technology. And perhaps as you press the accelerator of future electric car or store solar energy for a rainy day, you will have a richer appreciation of the science that makes that possible. A triumph of first principles transformed into technological power. In conclusion, supercapacitors exemplify how deep scientific understanding leads to revolutionary applications. They have come a long way from the Leyden jars and condensers of old. With continued innovation, these devices are set to play an even bigger role in the transition to sustainable energy by complementing batteries and enabling new feats of power delivery. As we close this 1 hour deep dive, you can confidently say you have mastered the key ideas from this book. From double layer capacitance and pseudo capacitance to materials, mechanisms, and real world performance. The next time you encounter the term supercapacitor, you won't just think fancy capacitor. You will envision the microscopic drama at electrode surface, the legacy of Faraday and Helmholtz, and the bold engineering that together make the supercapacitor a true superstar in the energy storage world.